Today we'll take a look at two very, very important concepts. One is called generative models. Okay, and the second thing is I will introduce TensorFlow to you. Some of you have been programming in TensorFlow, but I'll give you my way of programming in it so that you can create more controllable, flexible models and verify them. So in my opinion, there's from a research, from a investigation point of view, there's a better way to write TensorFlow than a lot of the examples you see over the internet. So I'll show you the key concepts, and so that from now on, all the assignments that you will do will be in TensorFlow. So the hard part is over. But you still have to program the CNN. So don't forget, because I don't know if you guys watched that Star Wars movie a long time ago, where they say you are not a Jedi yet. So same thing. If you wanted to be a Jedi in deep learning, you have to be able to program a CNN by yourself. Okay. So side by side, you will do this. Today, I'll give you another assignment based on TensorFlow, and I'll give you a handout as well. You'll first recreate the example that I did, then you will follow the theme and create your own enhancement of it, right? Okay, so coming to generative models, see, in deep learning, we go into typically two categories. So we have what we call discriminative models and generative models. So discriminative is what we have been doing before, where essentially we are interested in doing some kind of classification. We can also do what's called, what's the word for it, where we, okay, it will come to me in a second. Anyway, generative models, we have a couple of very, very interesting ideas, a lot of papers, a lot of research going on in this field. One are called variational autoencoders. And one are called generative adversarial networks. And sometimes we combine both of them. So today I will describe all the theory, the motivation behind variational autoencoders, and hopefully you'll be able to follow it. I'll also show you the code, and once we go through TensorFlow, you'll see it will make sense. Okay. Then generative adversarial networks, like I said, is also a similar idea, but has slightly different applications. But anyway, you'll see this is abbreviated as GANs, and this is abbreviated as VAEs. Okay, the reason we call it generative is because, as you will see, we can generate artificial data using these. So they have very, very interesting security and data-related applications. For example, what if we wanted to train a deep network, but we don't have enough data? Okay. Remember, deep networks, we have a lot of parameters. And typically, the general rule of thumb is that the training data has to be far greater than number of parameters that we are optimizing. So if we have 1 million parameters in a deep CNN, then our data should be, at least 100 million or more. So, anyway, let's come to VAEs. Let me explain the idea. We'll go over the math, which I showed you the handout. Hopefully you guys have gone through it. So, and hopefully today will make sense. So as far as VAEs are concerned, okay, there's a couple of ways of looking at it. Okay, one way is, so first of all, they are autoencoders. And as we already discussed in the last lecture, what's the job of an autoencoder? Autoencoder takes some data, compresses it, and then decompresses it to the exact same data. Okay. The idea in a variational autoencoder is that after we have learned the compression and the decompression, what if we can vary it a little bit? So vary the compressed data, and from this variation of the compressed data, we can create new data on the output without worrying about giving it any input data. Okay? So there's some very, very important mathematical concepts involved over here. How do we vary it? You know, it's not like you can take 0.5 if what was one of the compressed data was 0.5 and change it to 0.4. It will do something because we want to do it in a meaningful way. For example, if we were compressing the digit 2, okay, and this was producing the same data, we want to change it so that it still becomes 2 like this or 2 like this, right? Not just, you know, some output which doesn't even look like a number. So how do we control the, this is what we call the hidden space or the latent. So latent is another word for hidden. So we want to be able to vary the latent space so that we can generate meaningful data on the output, right? So towards the end of the last lecture, I talked about a few important concepts. So let me go over those very, very briefly again. One of them was the Bayes rule. Okay. So according to the Bayes rule, if you are given probability of A given B, this is P B A, P of A over P of B, right? And then there's few terminology that we should remember. One was, this is called the prior. So this is, and this is called the evidence. So the prior and the evidence are not conditional probabilities, okay? Meaning there's no condition. So this is basically previously known fact about our data, okay? This is based on what we are targeting. This is previous information that we have. So evidence and prior are both past information in a way, but, and this, if you recall, was called the likelihood. And lastly, this part is called the posterior. Okay, as we go along, hopefully this will start to make more and more sense. So from a variational autoencoder point of view, the key problem is like this. So first, let me explain the problem, then we'll try to solve it first mathematically, then show you the code, how it is able to do what we said in math, okay? So let's say this is the encoder. Okay, we give it some input x. Okay, in the terminology, we can call it anything we feel like it, but typically we use the letter z, z as our latent variable, or the hidden variable, or the compressed variable, however you want to think of it. Okay, so then we'll pass it through a decompressor or decoder, and we'll get some reconstructed x back. So the goal is this x should look similar to x, right? Okay, now if we knew the distribution of this, so let's say this is pz given x. So for a given x, it produces some distribution z given x, okay? If we knew the distribution of it, then after this is trained, right? So in plain English, if we know the distribution of PZ given X, then we can sample from this distribution and generate new data. Okay, so this is what we are interested in. Okay, as an example, let's pretend somehow this turned out to be a Gaussian distribution. Okay, so somehow this turned out to be a Gaussian distribution. Let's take a very simple example of test scores so that you can relate to it. Suppose the mean is 70, some kind of a standard deviation over here, right? So if we already know this is Gaussian distribution, it's easy to sample data from it. For example, if I wanted 10 samples out of this Gaussian distribution, they might look something like this: 40, 50, 60, 65, 68, 73, 75, 80, 90, something like this, right? And a few other numbers. You can see most of the data is distributed around the mean, right? So that would be a valid sample, okay? So anyway, if we picked one of these, like I was joking with you, you know, suppose these are our athletes, these are our nerds, whatever. So then, you know, based on what we give over here, it will produce correspondingly. So if I gave it 42, if this was following a normal or a Gaussian distribution, then obviously so if 40 was our training data's output, then even though 42 was never given to us as a compressed data over here, because no data produced a compression of 42, but we can artificially feed 42 over here and have it generate an output, and most likely that output will look similar to what the input of 40 produced over here. Okay, so once again, this does not have to be a Gaussian distribution. It could be beta distribution, gamma, whatever. So it doesn't matter what the shape of this distribution is. Point is, if we know this, then we can sample from it and generate meaningful artificial data, right? Okay, so now let's focus on this part. So according to probability theory, PA given B is also P, A, and B, which we typically write A comma B, okay, over P of B, okay. And again, it's very easy to understand. Let's say this is A, this is B, right? So we are saying probability of A given B, which is essentially so it will be basically the ratio of this divided by the B, which intuitively makes sense, okay? Now, sometimes we don't know the individual distributions, okay? For example, we don't know the Z distribution until we have created the encoder. There's an alternative formula to this, or let me put it this way. This is equal to P of AB over integral of PAB. So this is basically called the joint PDF. Some of you who were in this morning's computer vision class, we took an example of joint PDF with how it's computed, right? But anyway, so then basically, or let me show it to you in this form. So that you can understand. So this will be over the B variable, okay, over the A variable so that we get the data. So PZ given X, according to the laws of probability, will be PZ Cx, z and x, and integral of pzx integrated over x, let's see, we were dividing by b, so should be z, dz. Okay, so anyway, the problem, so once again, the goal is like this. The goal is we want to know this. And like I said, it doesn't matter what distribution it follows, whether it's uniform or Gaussian or whatever. If we know this distribution, then like I said, we can sample and create output. But if we don't even know what pattern it follows, then whatever samples we do will be basically creating meaningless data. Okay. So for us to be able to determine this, the issue is this part over here. We need to know the joint PDF between X and Z. Okay. But once again, we haven't even created the encoder yet. So this makes it very hard to create. So this becomes basically the unknown over here. Or I shouldn't say unknown, this becomes, so this is difficult to estimate. Okay, so there's a concept in advanced statistics called variational inference. Okay, so in variational inference, the idea is like this. If we have a distribution like this, that, as we said, is very difficult for us to determine because we need to know the joint PDF, which even if we give it a few samples, then try to estimate it, it will be a very poor estimate. Okay, so in variational inference, the idea is like this. We try to estimate this via a known distribution. Or in other words, think of it this way. We try to make this follow a known distribution. Okay, how? I'll give you the technique in a minute. Okay, but let's pretend somehow we can force this to follow another distribution. Okay, somehow we can force this to follow normal distribution. Okay, then if this now starts to behave like a normal distribution, then can we sample from here and generate meaningful data correctly, right? Okay, so now let's take a look at the goal. How do we make it follow a normal distribution? Okay, see, the general rule in deep learning or machine learning is, come up with a cost function, come up with a loss function. And then as we try to minimize the loss, it will accomplish whatever we are trying to make it do. So in this case, as you can see, one of the goals of the loss function will be to make this follow normal distribution. But that alone will not be very meaningful. We can make it follow normal distribution, but this may end up destroying the reconstruction part. Okay, so essentially, as you can intuitively see, so let me write the goal in plain English. Okay, so goal in plain English would be make p z given x normal distribution, or doesn't have to be normal, but any distribution that we can easily sample from, okay? Plus, make sure x prime is similar to x. Meaning, remember the purpose of our decoder is so that we can reconstruct from the compressed data. So if we can't recover x, then that will be terrible. So if together we made this as a cost function, okay, then we started back propagation. We have some data. So we forward propagate, back propagate, keep reducing the cost. Ultimately, it will set the weights over here, set the weights and biases over here. And now our decoder will be ready. Once the decoder is ready, we'll remove the encoder, sample from a normal distribution. If we had forced it to be a normal, then we can generate artificial data, right? Okay, so once again, easier said than done. So this looks like, you know, we can accomplish this, but like I said, there's very, very interesting detail over here, which no matter how many articles you read, you'll end up missing the point unless, you know, you go and try to understand variational inference. But anyway, let me give you one more point, one more background over here. And then we'll take a look at the derivation, and hopefully everything will make sense. Okay, so another background that we need is in generative models. Okay, our goal is to maximize P x1, x2, xn given theta. Okay, so let's try to see what do we mean by over here. Okay, x1, x2, xn are basically our training data. Okay, what's theta? Our model, which in case of a neural network will be weights and biases. So essentially what we are trying to say is, can our model generate these correctly? So is the probability of generating this from a model as high as possible? Okay, again, to give you a very, very simple explanation of it. Okay, let's forget the deep networks for a while. Okay, let's pretend our goal was, our model is basically Gaussian distribution. Okay, Gaussian distributions has some mu and has some standard deviation, right? Okay, so suppose the data that is given to us happens to be 40, 50, 60, 65, 67, 70, 73, 77, 82, 90s. So this is how the data look like, right? Okay, so there are many models that can fit this data. So one of the models, let's suppose model 1 is mu of 40, sigma of 10. Model 2, as an example, is mu of 70, sigma of, let's say, 15. Model 3 is, let's say, mu of 85, sigma of 5. Okay.
So what do you mean by model after training?
No, let's pretend these were 3 models given to us. So these are not neural networks. Their goal is simply to tell us whether this data follows a particular distribution. So you have 3 choices, pretend. How we got those, don't worry about those. So one of the choices is this, one of the choices is this, one of the choices is this. So my question to you is, if I gave you this data, which one of these three models will produce the highest probability given data for that given, given that model? Which one will match this data better?
Calculate mu and sigma for the better?
Third or second?
True.
By looking at the data, I mean, we can calculate the mu and sigma exactly, but just approximately, which one does it look like?
Second.
Second, right? So as you can see, the second one will produce a high value of this as compared to model 2 and model 3. Okay? So if the x's are independent, then this could be written in probability theory as P of xi given theta. Okay, I equal to 1 to n, as meaning it's a product of the individual probabilities. Okay. So once again, which model will be best? Whichever produces the highest value of this conditional probability, right? Okay. So in generative models, okay, pretend you have 1 million of these. What does the probabilities value range from?
From 1 to million if there is
0 to 1.
0 to 1. So what will happen if you multiply 0.9 times 1 million? It will go to 0, right? Because anything less than 1, you keep multiplying it, it keeps getting smaller and smaller. Okay, so the goal of maximizing this in terms of a product, like I said, will easily run into calculation round-off errors, meaning this will keep getting smaller and smaller. So alternatively, what we do is we don't try to maximize this probability in terms of the product. We try to maximize log of P x1. Okay, given a model, of course, that's implied. Okay, so if I take the log of both sides, right, what will happen over here? So if this was Px1 given theta multiplied by Px2 given theta multiplied by, right, because that's what the product means. If I took the log of it, what happens? Remember, log of A times B is log of A plus log of B. So this basically changes to a summation. Okay, so in short, this is called the log likelihood. Okay, so to summarize, what I'm trying to say is for generative models, we try to maximize log of P of x. Okay, whichever model produces that highest probability is the best model. So far, so good? Okay. Now let's put all of this together. So I'll take you to the handout. We'll go through, combine all these concepts together to come up with our goal over here. But this was in plain English. We'll put the goal now in exact mathematical terms. Then we'll translate to code, and you'll see how that works.
So the job of GAN is to generate artificial data, right?
Correct. In a certain way, and how we'll cover it in detail. Today, like I said, if we understand BAEs nicely, GANs will become pretty easy. Okay, so I'll take you to the handout I gave you last time, which was the variational autoencoder handout. Okay, so anyway, same picture that we drew over there, right? Okay, so given an input that follows some distribution, Z may follow some distribution P of Z, but anyway, this will be P Z given X. So as we feed in some X, the distribution over here will be indicated by P Z given X, right? And like I said, this cannot be computed, cannot be estimated easily. And one of the reasons is because PZX is unknown. The joint PDF is unknown. Okay, so this is where we'll use variational inference. So use variational inference, meaning try to approximate it by another distribution. Okay, so suppose this PZ of X, which we do not know, we wish to know this. So we wish to know this, but let's pretend we will try to estimate it using the variational inference principle by some QZ of X. Okay. Keep in mind, normally when we deal with probabilities, we always put P and P. So Q over here basically tells that this is basically a model that is generating it, like the encoder over here, for example. So not necessarily a probability distribution. It can be, but doesn't have to be. Okay. Okay, so now let's take a look at our development. Okay, last time, if you recall, if we are given two distributions, let's say P of X, P of Y as an example, right? Okay, how do we know the two distributions are similar or not? The similarity is defined by what we call